Hi, this is Melissa Langston, Associate Professor of Chemistry at Delaware Valley University. I'll be explaining atomic absorption spectrophotometry today and including a demonstration to determine the concentration of zinc in unknown solutions. So to start off, this is our PerkinElmer AA Analyst Atomic Absorption Spectrophotometer. To use the instrument, first we would turn on the power by hitting the toggle switch there, and we would also make sure to open the gas cylinders, in which we have a cylinder of compressed air, which is opened here as well as at the regulator, and then we also open our tank of acetylene using the top. From there, we'll have the opportunity in the instrument software to select the lamp that we're interested in, and of course today we're looking at zinc, and so that has been selected. The way that the instrument works then is that it will turn on the zinc lamp, and in doing that, what's going to happen is by looking at our lamp, a hollow cathode lamp, as shown here, this is one for aluminum, we see that there's an electrical connection. The electricity then flows into the hollow cathode lamp, in which it then has to make a jump from an anode to a cathode. As the electricity makes the jump from the anode to the cathode, we see that the flow of electrons then ends up ionizing the inert gas that's located inside of the hollow cathode lamp. Typically we see that this is argon. The argon, for example, gas then becomes ionized and starts to move about rather energetically through the hollow cathode lamp. That movement eventually causes argon ions to strike the cathode, which is made up of our metal of interest. That impact causes the metal of interest, or the cathode, to eject electrons, or rather photons, that are characteristic to that particular element. And so today, if we take a look inside here, we'll see that our zinc lamp is undergoing that process, which is called sputtering. And so around that zinc lamp, you can see that there's that nice pinkish purpley color. That pinkish purple color is the result of sputtering, and thus we see that there's a beam of light that's generated that is characteristic to zinc. And so those specific wavelengths that are being emitted are just characteristic to our zinc element. Now that beam of light then is directed out of the slit shown here and then across what is the burner head of the instrument. And so you can actually see that beam of light is passing over the burner head and will eventually exit over here. What's going to happen at the burner head is that there's a flame that is generated. And so our flame is made up of acetylene and air coming from our tanks. And we have the opportunity to do a couple things. From the software here, we can hit the flame tab and we can actually change the fuel to oxidant ratio, trying to get the maximum amount of absorbance. We also have the ability to change the oxidant. We are using air. Some people also use nitrous oxide as well. It generates a higher temperature flame. With that in mind, we can now actually turn the flame on. And so I'm going to hit the little toggle switch here. And I'll see that there's a striker in the back. And now we have a flame, an acetylene air flame. So if you take a look at the flame there, what's going to happen is our beam of light is actually passing through that flame. Our sample will be introduced into the system here through the capillary tube. And so as that sample goes into the capillary tube, it goes through the nebulizer to create that sample as an aerosol mist. That sample then becomes dried, and so we have a waste container to collect any solvent down there. We also will then char the sample. That's important because we are then breaking any bonds that are within our sample, and eventually we'll atomize that sample. The atoms then of whatever our sample is will go into the flame. Those that are zinc will absorb the wavelengths of light coming from our zinc hollow cathode lamp just over there. And so that is the signal that we're able to detect, and what we're essentially looking for is the difference in intensity from our hollow cathode lamp to what eventually gets to the detector. So very similar to UV-Vis spectrophotometry. And so the samples that we have here today, we have a spectrophotometric blank. We have 1, 2, 3, 4 standards. I have a sample of apple juice. I used some of my kids' juice boxes. It's the Honest Kids Happily Ever After juice. We also have a spiked sample of apple juice that we'll take a look at. And then we have a solution, or rather a sample of one of my least favorite wines, Sutter Home Pinot Grigio, which we can look for any zinc in there. And so to do that, now that we have the instrument running, and I should note a couple things we can do to set up things up and get the optimal settings. We can again play with that fuel to oxidant ratio within the software here. We can also change the height of the burner itself. Different points of the flame will be different in temperature, and thus we want to be able to have the hottest flame possible. And so that's one way that we can do that. And so we could do that. There's a knob down here that we can turn to adjust that, but the settings have already been optimized, and so we'll just go with running the instrument itself. So what I'm going to do here is come over to the Analyze tab. And so I'm going to try and treat everything as a sample. And so while I can tell the instrument what's a blank, what's a standard, I'm only going to ask everything to be a sample. And so the first thing I'm going to start with is our blank. And so I'll take my blank, insert the capillary into it, and now you see that the flame changes. You can also hear that that's different as well. Our sample is being fed up through the capillary into the nebulizer, into the flame. Our zinc beam of light is then passing through that. And so over here in Analyze, I'm going to hit Analyze Sample, even though I know it's the blank. And so I see that there's a progress bar that's given to me. There's a read delay. That's just to make sure that the sample is getting up and into the instrument itself. We're measuring. The instrument measures in triplicate. And so we'll see that we get a mean for our sample. We have a standard deviation and RSD, and then we also have the 3 replicate measurements that were made. So we want to record that, and I'll make sure that we record that. But for sake of time here, let's just keep rolling. We're going to look at standard 1. If I can get it in. And so we hope that the blank is our low value there. Meaning that now that we're looking at samples that we know have zinc in them, we should see that we have to get some higher concentrations from that, or higher absorbance values from that. And it looks like we do. That's our first standard. Sorry about the bobble. Our second standard is there. Analyze sample. And so with the data that we're able to collect from our standards, what we hope to do is essentially just make a Beer's Law plot so that we have the absorbance values through our measurements. The concentrations should be known, or at least can easily be calculated from the data that you have for C1V1 equals C2V2. And then based on our Beer's Law plot and the trend line that is applied to it, we should then be able to calculate the concentration of any zinc in our unknown solutions. And this, sorry guys, is not easy to do with just one hand. Let's hit Analyze Sample. This is actually our last standard, standard number 4 that we're looking at now. Alright, so that takes care of all of the standards. I'm going to run the blank again. It's nice to intermittently run the blank.